Swayam Prabha. Digital India. Educated India.
Which is going to give us the minimum objective function at the end of first iteration. So once we get this point, now we have to again do the exploratory search along the first variable. So the first variable, if we search, one point is this, another point will be somewhere here, and this point yielded the minimum objective function, so we choose this, and then we move to the second variable direction and we choose 2 point. One is this and another is here, and once we looked into these two or these 3 points, we find that the objective function value is reduced or minimized at this particular location. So we choose this as the final point of the exploratory search, and hence, and then once we compare this point and the initial point, we see these 2 points are different, so it is a success. Now we need to establish the direction, so the direction is going to be this. Along this direction, if we try to do the pattern search, which is being shown in this second figure, so this is the point which we reached, and once we do the pattern search, we'll get to a point here, and this point is 3.02 and 2.06. So 3.02, 2.06. At this point, once we did the exploratory search again, we found that we are not getting any better point based on the step size we have chosen. We reduced the step size, still we couldn't find any better point. If we further reduce, we might get, but in this particular case we have reached the precision value which we want, and hence we are stopping at this point and reporting this point as the optimum point obtained after the Hook-Gibbs algorithm has been executed, and this is our final optimum point. So this is about the Hook-Gibbs method. The other method which we had indicated was the Powell's conjugate direction method. Now in the Hook-Gibbs method, we saw that we are going along the variable direction. So the variables are dictating how the directions are going to be chosen, and these directions are always going to be orthogonal. This method actually did not evaluate any other direction other than the orthogonal direction. When we have more than 2 variables, or in many cases directions which are not orthogonal or directions which are not exactly along the variable, can be useful, which means 2 variables together, the combined effect of the variable can be useful to identify the direction, or combined effect of more than 1 variable could be useful. So there is a need for such situation as well. The Powell's conjugate direction method is an answer for those type of situation. So the concept here is based on the conjugate direction. So the conjugate direction is about the 2 independent pattern search initiated from different location, and these 2 independent pattern search is going to lead to 2 different locations in a parallel subsearch space, and these 2 locations, if we find, then we'll see that the optimum solution is going to lie, or is expected to lie, within that conjugate direction. So for example, here we have the objective function values for the 2 variables, the contours of the objective function value. Now if we start from 2 different locations, suppose here, and try to go in certain direction. Suppose this is my direction, and I can see that if I reach at this point, I'll reach to the minimum location along this direction. Now if I choose another point and go parallel to this direction, and I may reach a point here where the objective function is going to be minimum. So the conjugate direction is going to be the direction which joins these two directions, which is like this. And it says that the concept here says that the optimum solution is expected to lie along this conjugate direction somewhere. So if we do a search along this direction, we move very close to the or at the optimum solution. So in this case, the optimum solution is here, and we can reach closer to the optimum solution by choosing two parallel subspace which have been started from two different points. Now, how should we choose these two parallel subspace? How should we guide these two location? This is where we can actually understand the concept of Hooke-Jeffs method, where we have selected the direction along the design variables or decision variable to start with. So if you are choosing a direction along the variable, suppose this is the better point which I have obtained. Now from this point I will move to the second variable direction, which is this. And if you look into these two lines, the parallel direction for this one would be again this one. So this two now becomes the parallel subspace or parallel search space for this particular problem. Now if we are not going along the variable side or along the variable direction, we can choose other direction. Before I come to that, let us see if these two are my parallel search space. Then the direction connecting these 2 points is going to tell us in which direction I should search to reach closer to the optimum point. If these two directions are not chosen, we can choose some random direction. Suppose this is my direction, then I need to choose another direction. Again, I can say some random direction which is orthogonal to this, which is not influenced by this particular direction. If we choose that direction and find an optimum location, and from there again I can choose the direction parallel to this, the original direction. So this will lead to another optimum point. So this is my first direction and this is the final direction, and these two directions are parallel, and hence the endpoints of these two directions can be connected to reach closer to the optimum solution. So with this concept, we'll look into the algorithm of the Powell's conjugate method. So in this method, we have to first select a start point which we are indicating at x0. We have to identify the linearly independent directions di for each variable. So if we have n number of variables, we are saying that we need n number of linearly independent directions. Then we also need to select sufficiently small number epsilon to use it as a termination criteria. Now once we know this, then we actually perform the simultaneous unidirectional search for the optimum location starting from direction di. We can always start as I equal to 1. Again, we need to end in that particular direction. So if we are starting our direction, first direction, so we should end up doing that in the first direction. So as I had said, I'll go back to the previous slide. So we started our direction, we looked into all the other direction, in this case 2 variable, only one more direction is there. Then again we need to do the search in the same direction. It could be either this way or this way to reach an optimum point which is going to give us two parallel subspace, or it could be like this. So any of the way, whichever direction we have started with, we should end in that direction. So if you are looking into the algorithm, we are exactly doing that. We are starting with our direction di and we are again ending with di. So the direction starts from di plus 1 will go to dn, then it will start d1 and again it will reach to di. At this point we are saying that let x be the solution or be the optimum point in the first directional search along di, and that is indicated by xi. And once we complete all the search along all the direction and reach our point or reach the same direction again for the second time, then we reach to a point called x2. So at the end of the first direction we are reaching to the point x1, and at the end of the final direction, which happened to be the first direction again, we are obtaining a point x2. These 2 points are going to give me the conjugate direction from the parallel subspace which is along the di direction, and this direction is going to be established as dc is equal to x2 minus x1. So that is the direction which we had indicated, that this is my x2 and this is my x1. So the direction or the conjugate direction is going to be this, and this is what is indicated by dc. Once we obtain the dc value, this direction, we have to see the scalar quantity of this direction, whether it is less than the precision or not. If it is not, then what we are doing, we have started the direction from a particular point, so we need to replace the direction starting from the end direction. So we are choosing the last direction which is replaced by the previous direction and so forth, and the first direction which we haven't used here, we are going to replace it after normalizing the conjugate direction by this method. So once we do that, we are going to step 2, and in this process it is clear that originally whichever direction we used to develop the parallel subspace, one of the direction has been replaced with another with a conjugate direction. So now let us look into this step, how it is going to work. By the way, if the direction, the scalar quantity of the direction happen to be lesser than the precision, then we are going to terminate and report the final point as the optimum solution with fxj as the optimum function value. So let us look into this example. It is the same objective function we are using, starting point 0 0, and for easy to understand, we have chosen 2 directions. The first direction is along the variable, the first variable. The second direction is along the second variable. We have chosen the precision 0.5. So once we search along the first variable, we can write the direction as this, and if we want to optimize the lambda value, there we can see that we are getting two lambda values. One is negative 3.06 and other is 3.40. So out of this we are choosing the positive values. The negative value is also the optimum point. At this point we are not choosing. We'll see into the graphical representation and you'll get the idea why we are not choosing. But for time being, we are choosing 3.40. So our point is 3.40 and 0. From this particular point, we again go for the second direction, which is D2, and once we try to find out the point by optimizing the lambda value in that particular direction, we get again two lambda values, negative 1.9 and 1.82. I'll explain about the negative 1.9, but at this point we are using the positive 1.82, and this is going to lead us to this new point 3.40 and 1.82. With this point, now we need to go to the parallel subspace of the first direction. So parallel subspace of the first direction, which means D1, if we do that, then our location is going to be like this, for which again if we transform our objective function, it will become a single variable objective function, and if we optimize the lambda value, again we are going to get the negative and 6.23 and the negative 0.35. Out of this we are going to choose this particular point. The representation of negative 6.23, you will see it in the graphical representation to understand that particular point better. Now for this particular point, we'll find that the new point x2 is going to be 3.05 and 1.82. So we have 2 points, this is one and the x1 point. So with the help of that we can always obtain the conjugate direction, which can be represented as this. The scalar quantity of the conjugate direction is this, which is more than the precision which we have set for our problem. Hence we need to replace the direction. So what we are going to do is, the last direction was D2, and in this D2 direction we are saying that it will now take up the initial direction which we had, or the first direction or previous direction which we had. So the previous direction D1, earlier D1 was 1 0 and D2 was 0 1. So this value is going to come to D2, which is being shown here, and D1 will take up the value of normalized conjugate direction, which is dc by the scalar quantity of the conjugate direction. So this is that value which is shown here. Now with this we'll start our search again for the parallel subspace. So first we are going to use this particular direction, and as we use this particular direction, again we are going to get two lambda values. We'll use only this one because this point will be leading us to the point which we have so far neglected or not used all the time whenever the lambda value was negative or higher so far. So with this value we'll get the new point as 3.02 1.996. Now from this location we are going to go to the second direction, and as we do the second direction, again we are going to obtain the optimized lambda value as two different values, and we are going to choose this particular value to obtain the new location. And from this new location we need to go along the parallel subspace of D1 and as we are going parallel subspace of D1, then we find that the lambda value is going to be 3.84 and 0.01. We are choosing this particular direction, and then with that direction we are getting the location as this particular value. Now at this particular value we are going to find the conjugate direction. So the x4 and the previous point was x3. So once we subtract, we get this as the conjugate direction, and the scalar quantity of this conjugate direction is less than the precision which we have selected, and hence we can terminate at this particular point. We are terminating and reporting x minimum as the last obtained best point, and at this particular point we'll find that the objective function value is almost equal to 0. So this solution, let us look into the graphical representation. So we started our solution from 0, 0, and we looked into the two direction, or we looked into the direction along xi, and which resulted into 2 points. One is here and another is here. If we compare between these 2 points, we'll find that this point is going to give us a design variable which is negative. Now in this particular problem, as we said, the x1 and x2 are certain input, and the two terms which we have in the objective functions are the error term, which altogether we want to minimize. Now x1 and x2 are the input. Input into a system is expected to be a positive, so we cannot go towards the negative side. So we are rejecting this particular point and we are choosing this one. Now once we choose this particular point, then again we are going along the two direction of the second. We are going to the second direction, and in the second direction the optimum points we find out again this location and this location. And these two location, if we compare, location is going to yield or require the second variable to be negative, and if we do not want or if our input cannot be in the negative, so we can reject this particular point and we can choose this particular point as our optimum point. Now once we reach there, we need to go towards the parallel subspace, so again we have to choose the same direction. So here, once we reach here, we are going to again look into the direction along x1, and the first direction is going to yield us 2.1 is here, and another point would be way to somewhere here, which probably we had seen earlier as well, and which is going to lead to a x1 variable as negative. And since we do not want the negative value, so we'll choose this one. So once we choose this one, we have two parallel subspace, this and this. So the point which we have for this two direction, this direction and this direction, the optimum point. So this direction, the optimum point is here, and this direction, the optimum point is here. So if we connect these 2 points, this is going to give me the conjugate direction. And once we get this conjugate direction, this becomes one of our direction which will be replaced, or which is going to replace one of the earlier directions which we had. So in the second case, when we are doing this search, we have one direction in this one, and we have the second direction which was along the first variable, which will remain as this. So if we do the search in this particular direction, we'll get a point which is from here to here. This is the optimum point, and then from here again we are going to look into the direction of the first direction, or the second direction, which is parallel to the first variable, which is with this, and from this location we'll be again searching in this direction, which will give us some point here. And once we get this point here, if we join the optimum point here and optimum point here, this will become my conjugate direction, and along that conjugate direction if we search, we'll get an optimum point as this particular location. And once we get this point as an optimum location, that is resulting us, or that is giving us the optimum solution. We, as the difference in this conjugate direction is minimum, so we are ending up at this particular location as an optimum solution. So I believe you have good understanding of the two pattern search methods we have discussed so far, and these methods are quite useful, particularly if we can identify the pattern of the objective function, and particularly the objective function exhibits certain pattern. It's not always the engineering optimization problem is going to exhibit such pattern, particularly if our objective functions are quite discrete and does not exhibit such pattern. This type of methods are not going to work. So it all depends on the problem which you have in hand and how you are going to solve it and what it indicates. We also can have certain problems which can give us certain direction in the form of first order and the second order derivative. So as we know from our experience that the first order derivative does indicate the slope or the direction in which the optimum value is going to lie, and if we can really use that in the process, we may able to reach the optimum solution faster. So how to use this direction using the first order and the second order derivatives, we are going to discuss about those methods in our next class. So till then, goodbye and see you in the next class.